Okay. Hi, in this project, we designed an agent-based architecture for automated PCAP analysis. Next slide. The system processes network traffic through multiple stages and applies protocol-level analyzers such as DNS, HTTP, and TLS. These are combined with agent-based reasoning to generate structured outputs and campaign-level insights. Next slide. Next slide. This slide shows the overall system flow at a high level. PCAP files are first ingested and preprocessed, where metadata is extracted and the data is prepared. The agent then acts as the central controller, coordinating different analysis modules. These modules extract protocol-level evidence, and the results are finally correlated into meaningful insights. Next slide. Building on that, this diagram shows the detailed architecture. After ingestion, the pipeline performs structure extraction using tools like T-Sharp to generate protocol-level evidence. This data is stored and organized into intermediate artifacts such as bundles and summaries. The agent then operates in the reasoning layer, where it coordinates, analyzes, performs correlation, and generates hypotheses. Finally, the system produces campaign-level outputs and structured reports. Next slide. At the top, we have the web interface built using Flask, which stream live updates directly to the browser. Next is the ingestion layer, where PCAP files are processed and metadata is extracted and stored in a SQ-like database. Then comes the extraction layer, which uses T-Sharp to extract structured events like DNS, HTTP, and TLS. This is the most computationally heavy step, so you parallelize it using multiple workers. After that is the AI reasoning layer, where we use Llama 3.1 running locally through ollama. The AI analyzes structured evidence and maps findings to the MITRE attack framework. And finally, we have the correlation reporting layer, where all results are aggregated into reports, timelines, and flowcharts. So overall, it's a full pipeline, from raw packets to actionable insights. Next slide. The agent uses multiple specialized tools to analyze different aspects of network traffic. For example, the DNS analyzer detects suspicious domains and abnormal query patterns, while the HTTP and TLS analyzers inspect communication behavior and encrypted connections. The beaconing detector identifies periodic callback patterns, and the threat intelligence module averages data and non-malicious indicators. On top of that, we use a local LLM to support high-level reasoning, such as generating summaries and mapping findings to MITRE techniques. Next slide. The key feature of our system is the agent's decision-making logic. Instead of a fixed sequence, the agent dynamically selects which analyzers to run based on available evidence. Outputs from each step guide subsequent analysis, enabling adaptive investigation. It also performs correlation and hypothesis generation to derive higher-level attack insights. Now I'll pass on the time to Mustafa, who will be sharing more about the demonstration of this agentic AI.
Thank you, Jeannie. So for the demo, we have actually, for the demonstration, before I go into the demonstration, I would just like to go about like what we have run the pipeline on. So we've run the pipeline in total of 119 files, around which they have about 4,900 network events, and we have coupled it into a bundle package of 52. So this data actually spans nearly for about 2 months, from December all the way to January. So this shows that the system is capable of handling large-scale real-world data into a single automated run itself. So before we jump into the demo itself, I just want to highlight what the system actually produces itself. So for the single run, we can see that the system is able to generate about 83 findings, including 10 campaign finding, which means in this case that the activity persists between multiple bundles itself. So out of these findings, 11 were flagged as a human review, which shows that the system is designed to support analysts, not blindly automate decisions. We also automatically map the findings to MITRE attack techniques such as T1071 or T1573, which are widely used in this industry. One of the key insights that we discover was the persistent attack target RDP over nearly 2 months, which shows that the system can detect long-term attack patterns and not just isolated events. So this So, so now moving on to the demonstration itself. So as you can see, we have created a, so I'll now walk you through the web application itself. We start off with the upload page, which is where the user can upload their PCAPs itself. Um, so basically you can just drag and drop your files here, and it's a very standard format. We can use a very standard format like .pcap or .pcapng files. So once the file has been uploaded, files usually appear in this table below. Um, with size and timestamp itself. So all of the 119 files that were provided to us have been already uploaded to this interface itself. So next, moving on to pipeline itself, pipeline control page, which is where the actual analysis happens. So here we can select which phases we would like to run. As Jeannie had mentioned, we had 11 phases that we have. So we can decide which phases we want to run. So the first four phases or the first five phases are ingestion itself. So if you have already done ingestion and created events and bundles itself, then we can just directly move on to running the AI section stages itself. So the system controls also allows us to add number of workers in for phase 5 because it's the most computationally expensive phase itself. At this moment, we can add in up to 4, 8, 16 itself in a multiples itself. And so this allows, so these workers basically run the processes the PCAP faster using parallel execution. Furthermore, we have toggles here for key features in the agentic mode, where it allows the system to activate AI reasoning. So instead of just detecting patterns, the AI is able to form hypotheses, they evaluate evidence, assign confidence, and map findings to MITRE tag itself. So it behaves more like a security analyst rather than a rule-based tool itself. So when we start the pipeline, we can see that the logs update in real time here. So once we are So we are able to see that the logs do appear here in real time, and we can use this to live stream and observe each phase itself. So moving on to the metrics itself. Once a pipeline finishes, we can see the metrics and shows the performance details of each run itself. So our last run took about, so below we can see our last run took about 1.5 hours to complete, as you can see here in the page itself. And it clearly shows that phase 5, the extraction takes most of the time, which matches the scalability challenges mentioned, which is going to be further mentioned and further on. So this helps us identify like where the bottleneck lies in and how to optimize the system itself. So now we move on to the results page. We can see that where the analytic outputs are shown. The system groups PCAPs into bundles which act like an individual investigation unit. In our case, we have generated 52 bundles itself. Each of the bundles show your number of findings, hypotheses, events analyzed, and runtime itself. So going further into just what each bundle shows, we can see like a full investigation report at the top. We do see summaries of our findings as well as events, and we can see hypothesis. So under our finding sections, we can confirm the security issues, security threat level, confidence level. Uh, yes, and confidence levels, and also show the MITRE attack mapping. And below these are hypotheses which are represented by AI reasoning process. These are potential threads that may not have reached the confidence threshold, but this shows that the analyst can review borderline cases instead of missing them on. Furthermore, we have a LLM reason. This is backed by LLM reasoning, as mentioned in the agentic portion. Instead of just black boxing, we are able to see how the AI is coming to conclusions, and there's a transparency and importance to this trust itself, trust and validation. So finally, we move on to master report because which aggregates everything across all the bundles. This gives us like a global overview of the investigation itself. So the executive summary that the system generates describes what has happened across the whole network, and this is useful for non-technical stakeholders. We also have the most important visualization tool here is a hypothesis timeline. Each point represents a hypothesis. The size indicates the confidence, the color indicates the severity, and the ring shows if human intervention is required itself. So, uh, yeah, yeah. So that's about it for the demo itself. Yeah. And sorry, we have one more key other feature in our demo, in our pipeline itself, is that we are able to generate a flow chart. Yeah, we are able to generate a flow chart in which we are able to see how each how the relationship between our findings and IPs are present. And at the very bottom, we are able to see which ranking about the rankings of MITRE attacks, top entities, and top findings are present. So all of these are automatically derived from the raw packet data itself. Moving on to the more detailed portion of our results itself.
Okay, so digging into the TOS findings specifically, the pattern here is quite striking. The agent identified 39 unique external IP addresses, making TOS connections to a single internal host 10.128.239.57, specifically on port 3389, which is the standard RDP port for remote desktop protocol. Every one of these sessions has no SNI, no server name indication in a TOS handshake. That's significant because legitimate TOS clients almost always include an SNI to identify the target server. When it's consistently missing, that's a strong indicator of automated tooling, a scanner, or an exploitation framework. On top of that, TOS was also seen on non-standard ports from the same host, and this activity persisted continuously for nearly 2 months. Looking at the table on the right, the IP 179.60.146.36 appear in 20 separate daily bundles, 194.165.17.11 in 19. These are the same external IP coming back day after day, and that's not random scanning, that's persistent targeted activity. Let me now walk through what the agent actually detected. There were 46 findings in total, split across two types. The largest category, category are external sensitive access mapped to MITRE techniques T1133, T1078, and T1021, which relate to the encrypted channel communication and application layer protocols. The second category, 15 findings, are suspicious TOS sessions mapped to T1071.00, oh sorry, T1071 and T1071, which covers DNS as an application layer protocol. The bar chart on the right shows how findings were distributed over time. You can see activity began in early December 2025 and persisted, with the highest concentration in the final 2 weeks of January 2026. That's 13 findings in the last period alone, suggesting that the activity was escalating rather than tapering off.
So now I'll be talking more about the key challenges faced. So next slide. Hello.
Hello.
Yeah, next slide. So firstly, processing large PCAP files is slow and uses a lot of resources, which can affect performance. On top of that, correlation is challenging because the evidence comes from multiple extractors and needs to be aligned by time and host and protocol. And although the system outputs normalized Zig and Suricata style events, the extraction pipeline itself still relies on fixed tools like cap infos and T-sharp. Next slide. Another challenge is that legitimate traffic like CDN software updates or internal APIs can sometimes look suspicious, leading to false positives. At the same time, stealthy attacks can evade behavioral detection by blending in with normal traffic patterns. On top of that, TLS encryption hides the actual payload, so the system can only rely on metadata like SNI certificates or traffic patterns for analysis. Next slide. Another limitation is that the extractors only provide evidence and metadata, not direct conclusions. So we need to combine multiple analyzers like DNS, HTTP, TLS, and IOC checks to form a final judgment. On top of that, the detection quality depends heavily on the PCAP itself. So if there are any missing packets or incomplete data, the accuracy can be affected. Next slide. One key limitation is performance. Large PCAP files take longer to process and require more storage. The pipeline also runs in sequential stages, which introduces additional latency. If we perform deeper analysis across more data and analyzers, the compute cost increases. So overall, there's a trade-off between speed, how much evidence we analyze, and the confidence of the results. Now I'll be handing the time to John, who will be talking to us more about guardrails and safety controls.
I will now walk through the guardrails and safety controls. To summarize it, agentic AI systems are powerful, but they can also hallucinate. And in a security context, that means they're reporting an IP address, a domain, or network port that was never actually in the data. If we act on a hallucinated finding, blocking an IP, raising an alert, escalating to an analyst, that's wasted effort at best and a false sense of security at worst. So that's why the grounding check is designed to test for every single evidence item the agent produces across every bundle. On the left, you can see an example agent finding. It says that there's a suspicious TOS session where temp 10.128.239.57 connected to 88.214.25.115 on port 34985. Confidence 0.75, MITRE technique T1573. On the right is what the raw PCAP events actually contains. There's a TLS event with exactly that source IP, destination IP, and port. The SNI field is null, and there's a matching flow event too. So in this case, they match, but the question is, do they always match? We also restrict what the agent is allowed to do. In our code structure, the agent follows a fixed investigation workflow, such as reviewing the summary first, then checking beaconing, DNS, HTTP, TLS, bad IP reputation, and finally correlating the signals before generating findings. The agent only uses predefined analyzers through the agent interface, so it does not bypass the system to directly pass raw PCAPs or query low-level data tables. In addition, external command execution is limited to the pre-processing pipeline, where fixed tools like T-sharp and Capifos are used. This makes the behavior of the whole system more controlled and predictable. So how does the validation actually work? It's a three-step process. Step 1 is indexing. For each daily bundle, I pass the raw events from the handoff JSON files. These are the events extracted directly from the PCAP files. Next, we build the lookup sets in memory, DNS domain names, TOS connection tuples of source IP, destination IP and port, flow pairs, and a full IP address registry. Step 2 is checking. For each evidence item in each finding, we run a source-specific check against that index. The logic is different depending on the layer, on the type. For DNS finding, we verify the source IP actually sent a DNS query in the raw events and that the exact domain name appears in those queries. For TOS findings, we look for the full three-part tuple source IP, destination IP, and destination port in the raw TOS events. For beaconing findings, we check that the source to destination flow pair exists in the raw flow events. And step 3 is recording. Each evidence item is stamped as either grounded or ungrounded. And any failure is logged with the exact reason, so it's fully auditable. Even with these controls, the system is still designed to assist analysts, not to replace them. High-impact claims or conclusions with limited support are flagged for analyst reviews. In the final report, we include not just the finding itself, but also the confidence level, evidence items, false positive risk, misdetection risk, and any limitations. This is important because forensic analysis still requires human judgment, especially for remediation decisions or attack attribution. So overall, the agent helps with correlation and summarization, while the final decision remains with the human analyst. 11 of 83 findings, okay, so for the human in the loop, 11 of the 83 findings auto-flagged for analyst review.
So moving on to cost and efficiency. Next slide, please. This cost is estimated based on CPU time since our pipeline runs locally instead of using paid cloud service. We assume a rate of 5 cents per CPU hours based on a full round time for about 94 minutes. The total cost per round is around 8 cents. So overall, the system is very low cost, and most of the cost comes from processing raw PCAP file rather than the agent itself. Next slide. The slides compares the baseline and optimized system performance. By increasing from 1 to 4 workers, the runtime is reduced from about 10 hours to 1.57 hours, achieving roughly 6.4 times speed improvement. At the same time, total processing time drops by 84%, while the number of findings increased by about 80%, showing a better coverage. Overall, this optimization significantly improved both performance and cost efficiency. Next slide. So this table shows the runtime breakdown of our pipeline. The full pipeline takes about 94 minutes end to end. Most of this time is actually spent in evidence extraction stage, which alone takes around 93.9 minutes, makes it the main bottleneck as we discussed during the demo session. In contrast, the later stage are very fast. Agent investigation take less than half a second, and campaign analysis is similar quick, both operating almost in real time. Finally, the synthesis stage take only 0.06 seconds, which is very negligible. Next slide. This slide summarizes the trade-off in our system design. For speed, we use parallel workers to scale processing across multi-bundles, improving performance on large datasets. For accuracy, we combine rule-based detection with LLM verification and grounding checks, ensuring findings are supported by evidence and flagged when uncertain. For cost, the system runs fully locally using a local LLM, which avoid cloud API costs and keep the overall core cost low. So now we will move on to the conclusion. So to conclude, our project built a fully end-to-end agent-driven pipeline for network forensic analysis. Instead of just processing PCAP files, our system transforms raw network traffic into structured and explainable insights. We achieve this by combining multiple protocol analyzers such as DNS, HTTP, TLS, and beaconing, and then use an AI agent to correlate this signal and generate investigation hypotheses. The key strength of our approach is that it's fully evidence-based and explainable. Every finding is grounded in actual network events, and we explicitly prevent hallucinated outputs. We also design the system with particular guardrails, including confidence scoring and human review for critical decisions. So the AI acts as decision support rather than a replacement. Of course, there's limitations. The system depends on PCAP data quality and encrypted traffic like TLS reduced visibilities. There are also trade-offs between speed, accuracy, and computational cost. But overall, our work shows that it's possible to build a scalable and explainable network forensic system using agent AI, helping reduce manual effort while maintaining reliability. And here's the end of our presentation. Thank you.